Pluto is a distant and mysterious dwarf planet, once a member of our solar system's planetary family. However, recent startling announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a shocking revelation. They suggest that this icy world is on a potential collision course with Neptune. But how could this happen, and what would be the consequences of such a massive event? Are we witnessing a unique astronomical phenomenon, or is there something more to this impending cosmic collision? Join us as we explore the potential effects of Pluto and Neptune. Pluto, a former planet that was demoted to a dwarf planet partly due to its peculiar orbit, remains a subject of fascination and study in the astronomical community. According to recent predictions by leading scientists, Pluto's trajectory is dangerously close to Neptune's. Neil deGrasse Tyson and Michio Kaku are both raising red flags over a possible collision between these two planets, an event that could pose a significant threat to Earth. How is such an event even possible? Pluto's orbit around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete a single revolution. Since its discovery in 1930, it hasn't even finished one full orbit. Its journey is distinguished by an extremely elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more peculiar is its inclination. Pluto's path is tilted 17 degrees from the ecliptic plane, a steep angle compared to the other planets. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune does, defying what we might expect from their positions in the solar system. This leads to a natural question: why hasn't Pluto collided with Neptune? The answer lies in gravitational influences from other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike the other planets, whose orbits lie in close proximity on the ecliptic plane, Pluto's path stood out due to its steep slope and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is a testament to the intricacy of space mechanics. The three-body problem in space, figuring out how three objects like Pluto, Neptune, and the Sun move and affect each other, shows that Pluto's orbit, due to their gravitational interactions, is technically chaotic. Minor deviations in initial conditions can lead to significant variations over millions of years. However, despite this chaos, Pluto's orbit has been found to maintain remarkable stability over extremely long time scales. Numerical simulations show that the gravitational influence of major planets like Neptune, Jupiter, and Saturn help keep Pluto on a stable path, even for billions of years. These phenomena are essential for maintaining the order and predictability of motion in the universe. Without these mechanisms, our solar system would be a place of much greater chaos. Pluto's orbit is a remarkable example of celestial mechanics, demonstrating both stability and chaos within our solar system. Its unique characteristics, influenced by the gravitational forces of neighboring planets, particularly Neptune, showcase the dynamic nature of space. Predicting cosmic events, especially those involving chaotic orbits like Pluto's, present significant challenges. These systems' inherent unpredictability means that long-term forecasts are often fraught with uncertainty. While numerical simulations provide effective methods for comprehending and anticipating the future paths of celestial bodies, they also highlight the limits of our predictive abilities. So why are astrophysicists only now raising concerns about a possible collision between Pluto and Neptune, despite all these stabilizing forces? Neil deGrasse Tyson and Michio Kaku, both prominent figures in astrophysics, have expressed concerns about a potential collision. If Pluto and Neptune were to collide, it would be a catastrophic and rare event in our solar system. The collision would release an immense amount of energy, likely shattering Pluto due to its smaller size and icy composition. Debris from the collision could spread across the solar system, potentially creating hazards for other planets and moons. For Neptune, such an impact could alter its atmosphere and possibly its orbit, depending on the specifics of the collision. Michio Kaku, a renowned theoretical physicist known for his work in string theory, brings a unique perspective to this debate. His views on the future of space exploration and the interplay between theoretical and cosmic physics offer deep insights into phenomena like Pluto's orbit. Understanding the complex gravitational interactions and orbital dynamics of celestial bodies like Pluto provides crucial insights for future space missions. This knowledge can help in navigating the solar system more effectively, predicting potential hazards, and planning missions to the solar system's outermost regions and beyond. The lessons learned from studying Pluto's orbit can also be applied to investigate other celestial bodies, offering a blueprint for how we might approach and understand distant worlds. When it comes to the physics of planets, celestial mechanics and theoretical physics are deeply intertwined. The gravitational dance between Pluto and Neptune connects directly to fundamental principles of physics. If a collision were to occur, it would be a defining moment in astrophysics, providing a rare observational opportunity with possible implications for string theory. String theory, a theoretical framework in which point-like particles are replaced by one-dimensional strings, seeks to describe the fundamental forces and matter of the universe. A high-energy impact like a Pluto-Neptune collision could create extreme conditions where effects predicted by string theory might become observable, such as the behavior of fundamental particles and forces under extreme gravity and energy. While the direct impact on Earth would likely be insignificant due to our distance, the scientific implications of such an event could be profound. It might deepen our understanding of the universe's most fundamental principles. Pluto's orbit continues to be a prime example of how celestial mechanics balance chaos and order. The gravitational influences of nearby planets, particularly Neptune, shape its trajectory in complex but stable ways. Yet the universe remains unpredictable, with many potential cosmic catastrophes still lurking in the shadows. One such danger includes rogue planets, celestial bodies that have been ejected from their original star systems due to gravitational disturbances or close encounters. These planets drift through interstellar space, potentially crossing into other solar systems. If one were to pass near another star system, there is a small chance it could collide with a planet within it. Space is full of surprises. And Pluto's dance with Neptune might be one of the most dramatic performances still waiting to unfold. The role of resonance, why Pluto hasn't collided yet. Despite the sensational concerns about a potential collision, it's important to note a key factor in Pluto and Neptune's celestial choreography, orbital resonance. Pluto and Neptune are locked in a 3:2 mean motion resonance, meaning that for every 3 orbits Pluto completes around the Sun, Neptune completes exactly 2. This precise timing ensures that the two bodies never come dangerously close, even though their orbital paths intersect. This resonance acts as a cosmic safeguard, preventing a direct collision. It's a striking example of how gravitational relationships can establish long-term stability even in what appears to be a chaotic system. When Pluto approaches the part of its orbit that crosses Neptune's path, Neptune is always in a different part of its own orbit, thanks to this synchronized timing. This elegant dance, choreographed by gravity, has likely persisted for billions of years. It's one of the reasons scientists remain skeptical about an actual impact in the near future, even though simulations show that tiny changes in the solar system over vast timescales could theoretically lead to instability. A cautionary tale from the Kuiper Belt. Pluto is not alone in its distant realm. It resides within the Kuiper Belt, a vast region beyond Neptune populated by icy bodies, dwarf planets, and other debris. These trans-Neptunian objects, TNOs, provide a glimpse into the early solar system's formation and dynamics. Many of these bodies also exhibit unusual orbits, some of which appear to be influenced by unknown gravitational forces. In fact, the strange clustering of certain TNOs' orbits is part of what led scientists to propose the existence of a hypothetical ninth planet, often referred to as Planet 9. If Planet 9 exists, its gravity could eventually perturb the orbits of Kuiper Belt objects, including Pluto, altering their stable configurations. In such a scenario, even a slight nudge could change Pluto's trajectory over millions of years, potentially increasing the risk of an eventual encounter with Neptune or another planet. Looking ahead, what we can learn from Pluto. The fascination with Pluto goes far beyond its potential for catastrophic collisions. Its complex orbit, distant location, and unique composition make it a window into the past and future of our solar system. Missions like New Horizons, which flew by Pluto in 2015, revealed a world of surprising geological activity, towering ice mountains, and a nitrogen-rich atmosphere, all unexpected for such a small and distant body. Future missions could help us understand not only Pluto itself, but also the forces that shape the outer solar system. As we refine our models and simulations, we'll continue to test the stability of orbits, the influence of unseen forces, and the long-term fate of distant celestial objects. In a universe governed by both order and chaos, Pluto serves as a reminder that even the most stable systems may carry within them the seeds of transformation. Incredibly vast and mostly empty, space makes the likelihood of a rogue planet striking another directly very slim. The sheer scale of interstellar distances and the relative rarity of planets in open space act as a buffer, preventing frequent collisions. The mysterious dance of Pluto around the Sun continues to captivate scientists, fans, and non-fans alike, offering a window into the intricate nature of celestial mechanics. Its classification as a dwarf planet sparked controversy and altered our recent understanding of planetary bodies. Revelations about Pluto's orbit have rekindled interest in its place in the solar system. Neil deGrasse Tyson and Michio Kaku, two prominent voices in astrophysics, have raised concerns about a potential collision between Pluto and Neptune, shedding light on the intricate dynamics in our cosmic neighborhood. Their warnings emphasize the importance of understanding the gravitational and orbital mechanics that govern celestial bodies' movements. Pluto's orbit, characterized by its eccentricity and steep inclination, defies conventional expectations and challenges our comprehension of planetary motion. Unlike the relatively circular orbits of its neighboring planets, Pluto's path is unique. Its trajectory intersects with Neptune's orbit at various points along its extensive journey around the Sun. The gravitational influence of other planets, particularly Neptune, plays a significant role in maintaining Pluto's orbital stability for millennia despite the chaotic nature of its path. Numerical simulations have revealed underlying mechanisms and patterns that help regulate its motion, preventing potential calamities caused by collisions with neighboring celestial bodies. The problem of three bodies in space, Pluto, Neptune, and the Sun, epitomizes the intricate interplay of gravitational forces and orbital dynamics that govern the behavior of celestial objects. Understanding this complex system requires sophisticated mathematical models and computational simulations, which provide valuable insights into the long-term evolution of planetary orbits. Pluto's status as a dwarf planet has sparked discussions about the criteria for planetary classification and the diversity of celestial bodies within the solar system. While its small size and distant orbit set it apart from the traditional definition of a planet, Pluto's significance as a celestial object continues to inspire scientific inquiry and public fascination. The study of Pluto's orbit extends beyond the confines of our solar system, offering insights into broader astrophysical phenomena and the fundamental laws of physics. String theory, a theoretical framework that seeks to unify the fundamental forces of nature, provides a lens through which scientists can interpret the potential implications of a Pluto-Neptune encounter. The aftermath of such a collision, characterized by extreme conditions of energy and gravity, could yield valuable data for testing predictions of string theory related to spacetime and gravity. Gravitational waves produced by such an event could carry signatures that either align with or challenge the framework of string theory, offering new avenues for theoretical exploration and empirical verification. While the likelihood of a collision between Pluto and Neptune remains speculative, the scientific implications underscore the interconnectedness of celestial phenomena and the dynamic nature of the universe. The study of planetary orbits, gravitational interactions, and theoretical physics enriches our understanding of the cosmos and informs future plans for space exploration. Pluto's orbit serves as a testament to the delicate balance between stability and chaos in the solar system, highlighting the resilience of celestial bodies amidst gravitational perturbations and orbital resonances. Orbital resonances, observed in systems like TRAPPIST-1, can induce rhythmic patterns in planetary motion, leading to long-term changes in orbital stability. The potential for rogue planets, untethered from stellar systems, to roam the interstellar void poses a rare yet intriguing possibility of collisions with other celestial bodies. While the vastness of space reduces the likelihood of such encounters, the existence of these wandering worlds underscores the dynamic nature of cosmic exploration and the necessity of ongoing vigilance. Astrophysicists and astronomers remain alert, observing celestial bodies in an effort to decipher the secrets of the universe and guard against potential cosmic threats. Technological advancements and the power of computational modeling allow scientists to simulate complex astrophysical scenarios, providing useful information about the dynamics of planetary orbits and the evolution of the solar system. The pursuit of knowledge reaches beyond what we currently see in our cosmic neighborhood, encompassing distant, exotic worlds and phenomena that challenge our understanding of the fundamental laws of the universe. Pluto's orbit, with all its eccentricities and anomalies, calls for investigation and inquiry, offering a glimpse into the wonder and complexity of the cosmos. As we peer into the darkest corners of space, we confront the vastness of the unknown and the infinite possibilities it holds. Pluto's mysterious circling of the Sun serves as a reminder of the secrets awaiting discovery and the boundless potential for scientific exploration in the ever-expanding frontier of space. In this unfolding journey through the cosmos, Pluto stands not merely as a dwarf planet on the fringes of the solar system, but as a symbol of our quest to comprehend the unknown. Its irregular orbit, distant path, and complex interactions challenge the simplistic models of planetary behavior that once guided early astronomy. Instead, it invites us into a deeper exploration, one that embraces complexity, nuance, and the ever-changing nature of the universe. As space missions become more advanced and telescopic precision continues to increase, our ability to observe and analyze the distant behavior of celestial bodies like Pluto will only improve. Missions such as New Horizons have already provided unprecedented detail about Pluto's surface features, composition, and atmosphere. These insights have not only reshaped our view of Pluto itself but also informed our broader understanding of planetary formation and evolution. Moreover, Pluto's interaction with the Kuiper Belt, a vast region of icy bodies beyond Neptune, opens another chapter in the study of solar system dynamics. The Kuiper Belt is a reservoir of remnants from the early solar system, and Pluto, as one of its largest known inhabitants, acts as a key to unlocking its secrets. Each observation of Pluto's interaction with other trans-Neptunian objects adds another layer to our understanding of cosmic history. The resonance between Pluto and Neptune, where their orbital periods remain in a precise 3:2 ratio, demonstrates an elegant celestial balance. This resonance prevents the two from colliding, even as their orbits intersect. It's a stunning example of how chaos and order can coexist in the universe, governed by invisible mathematical relationships that hold through millennia. The broader philosophical implications of studying such systems cannot be ignored. In observing Pluto's path and the gravitational choreography of our solar system, we are reminded of our own place in the cosmos. These distant, cold, and seemingly insignificant bodies stir deep questions about origin, destiny, and the laws that bind reality together. At the frontier of astrophysics and cosmology, Pluto serves not just as an object of study but as a reminder of scientific humility. It shows us that even the smallest and most remote components of the universe can yield profound discoveries. Every anomaly, every deviation from expectation, is not a flaw in the system but a clue to a deeper, more unified truth. As the universe continues to expand and reveal its layers, Pluto will remain a silent, icy sentinel, tracing its solitary arc through the darkness. Its orbit, though puzzling, reflects the poetic symmetry of a cosmos that is as beautiful as it is mysterious. In following Pluto's path, we follow our own, driven by wonder, bound by curiosity, and propelled by the unquenchable desire to know what lies beyond.